So, today's Wednesday. Monday, we started talking about elimination. I gave you some problems at the end and showed you how to do it. I'd like to cover that again and point out some features about elimination that perhaps I didn't cover, or maybe will be clearer to you now that you've done a couple problems. Elimination is, whether you use elimination or substitution on a two-equation, two-variable problem is entirely up to you. Some problems work way easier with substitution. Others, elimination is the only way to stay organized. So I will always give you that choice, use substitution or elimination. If you're doing anything with more variables, more than two variables, you're going to find that elimination is going to be the way to do it, because you'll just stay organized. Theoretically, you can do any problem either way, but it's just a question of what's the organization of it and how difficult is it to keep track of things. Okay, so with elimination now, I'm going to show you the steps, and this system of equations that's at the bottom there is what I'm going to use to illustrate what the steps mean. So I'll tell you what the steps are, kind of show you an example, and then in the next slide I'll show you yet another example of how this works. Okay, so the very first thing that you want to do is that you want to multiply one or both of the equations by some constant. So you're multiplying all the coefficients and the constant all the way through. And what your goal is to get the coefficients of one of the variables to be the additive inverse of the other. So in other words, if you have a 2x, you want to try and get a negative 2x in the other equation. Or if you choose to go for a positive y, then the other equation should have a negative y, that sort of thing. So with this first step, what I'm choosing to do is I'm multiplying the first equation by 2, and I multiply all the terms through, so I get 4x plus 2y equals 6. And you see I've reached my goal where I have this 2y and this negative 2y. So there you go. You have the additive inverse of of one of the variables in both equations. The next thing you do then is you add the equations together. And what this does then is it eliminates that variable that you chose. And this is where it gets its name from, elimination. So if I add those two equations together, what I'm going to get is 4x plus x is 5x, and then 6 minus 1 is 5. So I end up with the equation 5x equals 5. Divide both sides by 5, and I get x equals 1. So I have part of my solution here. Okay? You see what I'm doing there? I'm taking these two equations together. So I get 4x plus x, and then I take 2y minus 2y, and so the y's just go away, and then I have 6 minus 1, and so my equation then turns out to be 5x equals 5, and then simplify that to x equals 1. And then what I do is, using that variable that you've found, go back to the original equation, or in fact you don't have to go back to the original equation. You can go to any equation to solve for the other variable. All the equations that you've used, from the first one to all the simplifications and transformations, are all true for the same coordinate points. And so if you spot one that's really easy, let's say your original equations involve fractions, and you've eliminated those fractions and you have nice integer coefficients, and even better than that, you have one without a coefficient, it's just a 1, go back to that one. The danger here, though, is that if you've made a mistake, you're going to get the wrong answer. But in fact, if you've made a mistake, you have the wrong x anyway. So using the original equation only helps you a little bit. So in this case, I'm going to use the first equation. So I know x is 1, so I'm going to put 2 times x, which is 1, plus y equals 3. And so I have 2 plus y equals 3, subtract 2 from both sides, I get y equals 1. So my solution then is 1, 1. Now I'd really, really, really like you to make sure that you're answering these questions in ordered pairs like this. It is true, x equals 1, y equals 1, but by showing it to be an ordered pair, you're making that association. It's like at the very beginning you know, we have that brace around both equations. You say both of those equations, we're looking for what makes both of them true. This point makes both of them true. So this is just a nice, convenient, compact way and a standard way to write the answer. Now, after you do this, you probably want to check your results. And on these 2 by 2, when I say 2 by 2, 2 equations, 2 unknown systems, they're actually pretty straightforward. So you might think the check is pretty easy, but when we get into higher ones, you probably want to check it a little bit more carefully. You just put them back in the original equations. Now here, your original equations really are the ones to use, because if you've made a mistake, you could go back and just prove your mistake if you use some intermediate equations. So go back to the very original ones. In this case, since x and y equals 1, we say 2 times 1 plus 1 equals 3. That's true. And then 1 minus 2 times 1 is negative 1. That's true. So we're good. And then we're done. Now we can extend that to any number of variables. And so if we have more variables than 2, we just progressively eliminate more and more of the variables until we get down to 1 variable, and then we'll do something called a back solve. We'll get to that a little later today. Okay, so here's some examples using elimination. Okay, so the first step is I want to multiply the equations to get one of the variables with the additive inverse coefficient, and so I'm going to take that. In this case, I'm going to take both equations. You see, there isn't one factor that I can multiply either the first or the second one by to get something in the other equation. So I notice with the 3 and the negative 2, if I multiply the first one by 2, and if I multiply the second one by 3, I'll get to that coefficient of 6 in front of the y, 6 and negative 6. So I multiply the first equation by 2, and I get 8x plus 6y equals 16. And then I multiply the second equation by 3, and I get 3x minus 6y equals 39. So very clearly, we're not introducing any fractions, anything like that. We're not multiplying by a fraction. We're just multiplying by whole numbers to get to these nice coefficients. And so now when I add those two equations, I get 8x plus 3x equals 11x, and 16 plus 39 is 55. My 6y and my negative 6y cancel each other out, so I divide both sides by 11, and so my answer is x equals 5. So then I'll put the 5 in the first equation, so I have 4 times 5 plus 3y equals 8, and so I'll subtract 20 from both sides, and so I get 3y minus 11 equals negative 12. Divide both sides by 3, and I get y equals negative 4. So there's my solution, is going to be 5 and negative 4. Now, be very careful here. Sometimes you're going to solve for x, sometimes you're going to solve for y first, and so you get y first, and then you get an x. Don't mistake the order of the coordinate pair. Make sure that the x, in this case 5, goes in that first position, and the y, which is negative 4, goes in the second position. So I'll check them in the original equations, and lo and behold, I'm good. So 5 times 4 plus 3 times negative 4 is 8. 5 minus 2 times negative 4 is 13. And so we're good to go. Okay, not everything involves integer ratios, or not everything involves integers. Sometimes we get integer ratios, and sometimes we get decimal numbers for coefficients in front of these. In fact, probably decimal number coefficients will be the most common, because you make measurements and they almost never end up to be exactly an integer. But let's look at these integer ratios and say, okay, what can we do here? Now, the thing about when you're dealing with these kinds of systems, you don't have to do it all in one fell swoop. Okay, what you can do first is get an equivalent set of equations that doesn't have any fractions in it. So we can transform the first one by all the rules that you know that are legal transformations, and then transform the second one. Don't relate the two until you get all integers. So with that first one, it looks like I want to multiply that by 3 times 2 to eliminate the 3 in the denominator and the 2 in the denominator. And the second one, I want to do that with 5 and 3. And so when I do that, I say, okay, 2 times 3 times 5/3 is going to be 10, and then 2 times 3 times 3/2 is going to be 9. And then remember to do the other side, the constant side. So 2 times 3 times 11 is 66. The second one, we have 3 times 5 times 1/5 is 3. 3 times 5 times -2/3 is -10. And then 3 times 5, which happens to be 15, gives you a -31 for that second one. Now we have a problem that at least looks familiar. So we have all nice integer coefficients. Now if you have decimal numbers, you can do the same thing. You just, let's say if you have your decimals to 2 or 3 digits or whatever, just multiply it by 10, 100, or 1,000 to get rid of the decimals, and then you're dealing with larger integers, but nevertheless they're integers. And so when you go to do things like division and things like that, you don't have to worry so much about dividing numbers that are decimals. Okay, so with this we're going to choose to make a coefficient that will allow us to eliminate one of the variables. So on this one I chose multiplying the first one by 3 and the second one by -10. Multiplying by 3 is pretty easy. Multiplying by -10 is even easier. So I get these equations, and I have a 30x and a -30x, and this is exactly what I want. And granted, I have big numbers, okay? So it's possible that I end up with kind of a nasty ratio and things of that sort, but you're not changing your answers at all when you're doing this. And so don't feel panic struck if you get into numbers in the hundreds, because oftentimes if you have small integer solutions to this thing, all the division will work out for you ultimately. Okay, so I have these two equations, and I'm going to add them together, and so I'll get 127y equals 508, and then y equals 508 divided by 127, and I get 4. And so then I'll go back to one of my equations, and in this case I'm only going to use that, I'm going to use this equation to find out what x is, because that's an easy equation for me. I got 4 times -10 is pretty easy, and so these things, I substitute my y, which is known at that point, solve for x, and I get x equals 3. So my solution is going to be 3, 4, but especially in a case like this, I think I really do want to check it out. And of course I don't check it out here, at least I didn't take the space, but you would put those in, and so we can probably even do that mentally. So if we take 5/3 times 3, that's going to be 5, and then 3/2 times 4 is going to be 12, so we have 3/2 is 6. Oh no, it's going to be 5 plus 6 equals 11, so that one works. And then we have 3/5 minus, looks like 8/3, and that one will take a little bit of piece of paper to do, but it should work. Okay? Okay, so here's one for you to try. Actually, there's 3 for you to try. And try all of them. Talk to your neighbor if that helps. And I'll be passing out some papers while you're doing this. Okay, so we'll just kind of march through the solutions here. You may have done it slightly different, which is fine, so long as you get to the same answer. So we have y equals 7, -2, 7. At least one person didn't get it right. Okay, then the second one, we look at 1 3/2. Okay, everybody good with that one? And then the last one, 6 comma 3, and that checks out. Okay, so you see, unlike substitution, where if you look back at the work you've done with substitution, you'll have probably a bigger variety of the way the paper looks. Okay, and with this one, you see, almost down to the step, it's exactly the same, and that's the nice part about elimination. When you're doing it with multiple variables and things like that, you can stop. You know, if your phone rings or you get distracted or something, you can stop. You come back and you know exactly where you are and you know exactly how to carry on. With substitution, that's not always the case. Okay, so let's look at a few word problems. Now this one is a rate problem. And so what we have is a plane flying with respectable pilots. I'm not talking about Malaysia Air, right? No, that's in poor taste, I suppose. But anyway, so you're on a 3,000-mile trip, and one way it takes 6 hours, 15 minutes, and the other way it takes 5 hours. And of course, a plane flies, it measures its speed according to the airspeed, right? It's like when you're swimming in a stream, the stream carries you one direction and you can swim against it or with it, and so your velocity is either the sum of your velocity and the stream or the difference. And so here we have a fixed length. We know how long it takes to go one way or the other. And so if I draw up a diagram, this is what I have. So I'm going to make my diagram and, oops, it's not stopping for me. We'll start from the diagram. So I have wind going in a certain direction. I'm going to go both ways on a 3,000-mile trip, and I know my combined rate times time equals distance. Okay, so I'll make my definitions. P is my plane speed, W is my wind speed. So if I add the two together, that's my combined rate, and that's the faster rate, right? So it's going to take the shorter amount of time. This times 5 equals 3,000. And then when I set up the other equation, I get P minus W times 6.25 equals 3,000. Now, if you make a mistake on a problem like this, on a combined rate problem, what's going to happen is that, let's say, if the first one I made P minus W and the second one I made P plus W, I'm going to come out with a negative W. And all that means is that I got the direction wrong in it. So long as they're different signs, you're good to go with these. You're going to get the same pair of answers. If you set it up correctly, the positive direction of the wind will be the positive direction of your plane. If you get a negative number, then you've just messed up the sign. You'll still get the same numeric answer. So then I'm going to expand these, and I'm going to stop. So the first one is just simply 5p plus 5w equals 3,000. The next one, I'm not only going to multiply it by 6 1/4, I'm going to multiply it by 100 as well. So I have integers. 625p minus 625w equals 300,000. Okay, so I've multiplied the 3,000 times 100 as well. And so if I, now with my elimination, since I have two 625s and two 5s, I want to see, is one a multiple of the other? Well, you know it is, because 625 ends in a 5, and so it should be divisible by 5, so I want to see what that is. So I'll do some division, and you see that it's 125. So if I multiply the first one by 125, so this is the second equation, this one with a difference in it. This is the first equation. I've multiplied it by 125, so I get 3,000 times 125 is 375,000. So when I add the two together, my wind component drops out, and so I just get 1,250 equals 675,000. And so then I'm going to drop off a 0 off of both of these. Okay, so I'm just going to do my long division by 125 divided by 67,500. And so when I do my division, I get 540. So my plane speed is 540 miles per hour. And now what I do with that is I will put my plane speed in the simpler equation, and then solve for that, and I get my wind speed equals 60 miles an hour. So if I test it in the first equation, this works. Test it in the second equation, it works again. So then I'll answer in a sentence, the plane flew at 540 miles per hour, and the wind blew at 60 miles per hour. Okay, any question on this? Yes?
Why was it 625 when it was 6 hours and 15 minutes?
6 hours and 15 minutes? 15 minutes is a fourth of an hour.
Okay.
So I put it all in hours.
Okay.
Now you can do this whole thing in minutes, but then you get really, really big numbers, right? So, or you can do it in, 6 1/4, which is going to be 25 fourths is another way to do it.
Okay.
So now this kind of problem comes in a lot of shapes and forms. Sometimes it's a problem involving swimming. Sometimes it's a plane thing. Sometimes it's a boat in a stream. All that kind of stuff. But these are basically rate problems in one shape or another.
Question?
Yeah.
On the last one, why was the first one like P plus W and the other one was P minus W?
Imagine you're going from here to here at the same speed relative to the air, but the wind is going to push you along. So that's going to be P plus W is that rate. So when you're coming this direction, you're going to be going against the wind. So if you have your speed is P, then the speed with respect to the ground is going to be P minus W. So one of them you're going with it, so you add the wind speed. The other one you're going against it, and you subtract the wind speed.
It didn't matter which one was P minus W and P plus W. If you could do P plus W for this.
The difference is that I have two different times. I have 5 hours and 6 1/4 hours. So reason this as you're working against the wind, it's going to take you longer. Okay? Now, if I had swapped my signs right here,
Yeah.
the math would have looked different, but what I would have come out with is my plane speed would have been 540, and my wind speed would be negative 60.
Oh, okay.
Okay, so it will still work out. It's just that your convention on what's positive and what's negative is just turned around.
Okay.
So I guess the moral is don't worry too much about it, but if you get a negative number, it means that you've just started with one of the definitions in the wrong direction. Yes?
Can you explain the 625p plus 625, that step right there? How you go from negative to, or you subtraction to positive, and then where that 375?
These are two different things. So this one, okay,
Yeah.
is going to be this equation expanded and multiplied by 100.
Yeah.
Okay, so probably if I put my little grouping, these two go together. And then this particular one here, the next one, comes from that first equation. So this is this equation multiplied by, and that's why I did that calculation on the side, this 125. I multiplied both sides by 125. So 125 times 5 is 625. So there's my two coefficients with the plus. And then 3,000 times 125 gives me 375,000.
I see what you're doing.
So it's the transformed first equation.
Gotcha. So
Yeah.
we're doing it, but we were, yeah, I got you.
Exactly. Okay. And then we just add them together, and the W drops out because they're both 625. All right? So let's look at a mixture problem again. We've done a few mixture problems, and there's two ways to do these. And when you do it by substitution, you get back to the way that we've done it at the beginning of the semester. And when you do it by elimination, you just have an elimination set of equations. So let's look at this problem here. How many liters of a 40% alcohol solution must be mixed with a 65% solution to make 20 liters of a 50% solution? Classic mixture problem, right? Where we have two different concentrations. We want to end up with a known amount with a concentration of 50%. So first thing I do is I'm going to make my variables. Now, when we did this before, what we did was we took A as the amount of the first solution, and then we took 20 minus A for the amount of the second solution. But now, just to illustrate this, I'm going to use two variables and show you what happens here. So we have A plus B equals 20, and 0.4 times A plus 0.65 B equals 0.5 times 20. So on this one, the first one, I'm looking at my total quantities, right? The A and the B have to equal 20. And then this is the one that is the balance of alcohol. So the amount of alcohol that I'm getting from the 40% solution is 40% of A. The amount of alcohol I'm getting from the 65% solution is 65% of B. And then what I want to end up with is 50% of 20 liters is how much alcohol I end up total. So the first thing I'm going to do is I'm going to make that second equation into all integers, just by first multiplying 0.5 times 20, which is 10, and then I'm going to multiply everything times 100 to get rid of my decimal, and I have 40A plus 65B equals 1,000. So if I look at that equation plus the A plus B equals 20, I have my two equations. Now, if I did it by substitution, this is what I end up with. Whoops, wow, I hit the wrong button there. Sorry about this. Okay, here's where I want to end. Okay, so if I take that A plus B and I figure out B equals 20 minus A, I get this equation, and that should look pretty familiar because that's the way we did it with substitution. So we were implying the substitution before, and we can solve this then for A, and then we put the A in the original equation and we can get B. Or the other thing that we can do is we can have two equations, two unknowns, and use elimination. Gosh, I did that again. Well, I'll just leave it at the end of the slide here. I can do it by elimination. And so originally what I get with a substitution is I get to my A equals 12, and I know A plus B equals 20, so B equals 8. If I do it by elimination, what I do is I take this first equation, multiply it by negative 40 to get this equation here. So the negative 40A minus 40B equals negative 800. And then I add those two equations, the second equation plus this now transformed first equation. I get 25B equals 200. Then do the division. 200 divided by 25 is 8, and so I know A equals 12. So I get to the same answer. I'll let you digest that for a minute here. So really, if you just look at the amount of writing that's involved, both of them take about the same effort, and that's what you would expect with two equations like this. There's not a whole lot of complexity there. It's mostly dealing with the larger numbers. Once I got rid of the decimal, it's possible to do it with the decimal and not ever eliminate that. But with the elimination step, you'd probably eliminate it. Okay, any questions on this one? Did you get a chance to look at it? Yes?
Why is it, I don't understand I'm not following the elimination one.
Okay. What I'll do is I'll rewrite it on the board in the form that I've usually had. Okay, so we have A plus B equals 20, and you understand how I got to 40A, right? There's no problem there. Instead of, I multiplied by 100 to eliminate the decimal. Okay, so I have 40 plus 65B equals 1,000. Then the first thing that I did was I multiplied this by negative 40 to get negative 40A minus 40B equals negative 800. And then I added these two together. Okay, so the A's drop out, and I have 65 minus 40, which is 25. So I have 25B equals 1,000 minus 800 is 200. And so I have B equals 200 over 25. Okay, so that's just kind of reformatted to be consistent with what I had. Okay. So after elimination, let's look at what happens with more variables. All right, so the first thing I'm going to do is lay out a problem here, and I'm going to say I want to make this transformation, and I'll stop right here. This set of equations here is just 3 equations that comes from my problem. Okay, so I have x minus y plus 3z equals 5, 2x plus y plus 5z equals 12, x minus y plus 4z equals 7. So here's the value now of putting all the variables on one side in a nice column. You have this nice organized, essentially table that tells you the equations. Now, problems will seldom appear like that in real life. You'll usually get, variables all over the place, and you usually have to do a little bit of moving things around to get all the variables on one side, all the constants on the other. And in that process, you can, of course, do things like eliminate fractions or eliminate decimals, things of that sort. But you're going to get a system of equations that looks like this. So what we want to do is we want to transform this thing first and foremost into this form here. Okay, so notice the first equation is the same. The second equation does not have an x, and the third equation does not have an x and y, but it tells you what z is. Okay, so we're going to call that row echelon form. So once you're at row echelon form, we're going to figure out what the rest of the variables are. Now, after I do that, I'll go back to tell you how do we get from the general form into this row echelon form. But let's look at this the way it is. So I'm going to solve this first by noting that z equals 1, and then putting z by substitution in the second equation. So that second equation, 3y minus z equals 2, I know what z is, so I'll put the 1 in there. So I have 3y minus 1 equals 2, and so simplify that to 3y equals 3, y equals 1. So now I have 2 of my 3 variables. I have z equals 1 and y equals 1. And then I'm going to go to that first equation, and I'm going to plug in my known values of y and z, and so I get x minus 1 plus 3 times 1 equals 5. And then I'll simplify that. And I get x equals 3. Okay, so I've solved for all 3 variables now, starting from this point where I have this row echelon form of equations. So now what we want, ooh, gosh, I did it again. Okay, so now what we want to do is we want to check this, and I'm going to check it in the row echelon form. You really should be, at this point, checking it in the original form, but I haven't perhaps convinced you that that original one and the row echelon are the same. So really I'm just talking about the row echelon at this point. So I'm going to put all my x, y's, and z's in those equations. So the first equation will have 3 minus 1 plus 3 times 1, so that's your x, y, and z. That's going to equal 5, which is what the first equation is supposed to equal. The second one is 3 times 1 minus 1 is 3 minus 1, that's 2, so my second equation works. And of course the third one was virtually a given, where z equals z. And so here I'm going to represent my solution as ordered pairs again, and I'm going to use this x, y, and z. So if we're just using 3 consecutive letters in the alphabet, we just put them in order. So if my equation is in A, B, and C, then I'm going to write A, B, and C. But I always, if I want to have a different order or so, you can just write what the variables are as an ordered pair, like this, and then you say equals, and then their values, 3, 1, 1, like that. Okay? So if you end up with something like, let's say you're looking at length, width, and time, length, width, and time, then you would define it like this and then put your values in that order there. So this is kind of specifying what they are. But in all cases when we're using x, y, and z, we'll just designate that that's the order that we're going to put them in. And so the significance of x, y, and z, 3 variables, is that very often spatial problems are done in 3 dimensions, right? Like if we look at if we put a coordinate system on this room, we can specify, how many units in, how many units back, and how many units up, and so you can get to any place in any kind of a 3-dimensional space. So 3 variables, 3 unknowns is a real common combination simply because that's the kind of space that we live in. Okay, so, and I think I'm going to stop yes?
How do you get the row echelon?
How do you get to row echelon form?
Yeah.
Going to get to that.
Oh.
Okay, so I'm teaching you backwards.
Okay.
Any of you play a musical instrument? One of the things that I used to play in a few bands, and we had to crank out a lot of new music. One of the things that our band leader always felt very strongly about is that we start at the end of a song, and we learn the last part, and then we learn ahead, or we learn forward, because as you're going through the song, then you get to the places that you've been practicing more. And that's kind of the philosophy here, is that as we go along, we'll get more confident because we've practiced these last pieces a little bit more. But try that musically. If you learn a piano piece, learn the ending before the beginning, and you'll kind of get it'll be remarkable how well you learn and how fast you can learn the piece that way. Okay, so we're in math, we're not music. So I'd like you to try this one. Do the back solve. And then on Friday we'll talk about how to get to row echelon form. Okay, so first thing we do is take the z, solve for y, and then we solve for x, and we get our solution. So we take that z, we stick it in that second equation, 10y minus 3 times 3 equals 11. So we'll find that we add 9 to both sides, we get 10y equals 20, y equals 2. And then we'll put both the 2 and the 3 in the first equation. And we get to negative 1 for x. And then we can check just by sticking it in the original equations. And sure enough, we get what we expect. So the terminology here is that this is called back substitution, or the back solve. All right, so we're going to talk about how now to get from, on Friday we'll talk about how to get from that general form